Determine whether life ever arose on Mars has long been one of the most compelling questions driving space exploration. For decades, scientists have wondered if our neighboring planet once harbored living organisms, or if perhaps under the right conditions, it might still host them today in hidden places beneath its surface. To approach this question, researchers focus on identifying the conditions needed for life to thrive, drawing parallels with Earth, but also recognizing that life beyond our planet could be fundamentally different from what we know. On Earth, all forms of life need water to survive. Every plant, animal, and microbe that exists on our planet relies on water in one form or another. It is not simply a convenience, but the essential ingredient for biological processes. If life ever evolved on Mars, it likely did so in the presence of a long-standing water supply. Just as life on Earth first emerged in watery environments billions of years ago, that is why our search for evidence of life on Mars focuses on areas where liquid water was once stable on the surface, where it may still exist below the crust, or in current hotspots, where geothermal energy creates environments similar to the hydrothermal pools of Yellowstone National Park. Such hydrothermal pools on Earth are teeming with microbial life, showing us that hot, mineral-rich water can provide an environment where organisms not only survive but flourish. Data collected from multiple NASA Mars missions support this line of investigation, suggesting the presence of liquid water just beneath the surface in rare locations, as well as large amounts of frozen water locked into the polar ice caps. This discovery has been one of the most transformative in planetary science. Water ice at the Martian poles was once only suspected, but now it is confirmed. Moreover, evidence hints that thin films of salty liquid water may form under certain seasonal and geographic conditions. Each of these discoveries increases the odds that Mars may still be habitable in small niches, even if only for microbes. But water alone is not enough. For life to exist, energy sources are also required. On Earth, the vast majority of living things depend on the sun's energy through photosynthesis or food chains based on plants.
However,
life on Mars' surface is unlikely because the thin atmosphere allows harmful radiation and superoxides to reach the ground. These chemical compounds break down organic molecules, the very carbon-based building blocks of life, before they have a chance to accumulate. That is why the surface appears so hostile and barren. Yet, life on Earth has shown remarkable adaptability. We find living organisms in places with no sunlight at all, in the pitch-black depths of the oceans near hydrothermal vents, inside the pores of solid rock, and deep beneath the crust where heat and chemical reactions sustain life. Chemical energy and geothermal energy are just as valid as sunlight when it comes to fueling biological processes. This gives scientists hope that if life ever took hold on Mars, perhaps tiny subsurface microbes adapted to darkness could have used similar energy sources to persist. Searching for life is not easy, even here on Earth, where we know what life looks like. Differentiating life from non-life is a scientific challenge. On Earth, we rely on familiar markers called biosignatures, chemical patterns, molecular structures, or even fossilized shapes that point to biological activity. But life on another world might not follow Earth's template, could be different in chemistry, structure, and physical characteristics. For this reason, researchers are developing life detection technologies designed to identify life in non-Earth-centric terms. These instruments aim to detect the universal hallmarks of living systems, even if the life forms are utterly alien to us. In the meantime, NASA's Mars missions focus on looking for the telltale biosignatures of current and past life using available tools. One key approach is to study the location and form of carbon on Mars. Carbon is a fundamental building block of life, and understanding where and how it exists on the planet could reveal much about the potential for biology. Currently, Mars' thin atmosphere is composed mostly of carbon dioxide. But if scientists were to discover carbonate minerals on the surface rocks formed by chemical reactions between carbon dioxide and liquid water, it would suggest that water had been present for long periods. Long-standing water environments are crucial because they could have given life enough time to emerge. Clues may also come from geology. By studying fossils and sedimentary rock on Earth, we know that only certain environments preserve the record of past life well. Calm lake beds, shallow seas, and river deltas often trap organic remains and preserve them in fine sediments. This is why Mars exploration targets ancient lakes and streams. If similar deposits exist on Mars, They may hold microscopic fossils or chemical traces of organisms that once lived there billions of years ago. The rocks of Jezero crater, for example, are believed to have formed in a once thriving river delta, making them prime candidates for study by the Perseverance rover. Understanding the climate of Mars is another vital piece of this puzzle. Today, Mars is cold, dry, and seemingly lifeless. But the story of its climate is complex, and scientists seek to characterize both the current Martian climate and its ancient past. So what is Mars' climate like today? The red planet's climate is largely controlled by the seasonal cycles of carbon dioxide, dust, and water vapor. Every winter, carbon dioxide at the poles freezes into thick ice caps, only to sublimate back into the atmosphere during spring and summer. This exchange between ice and air creates large seasonal swings in atmospheric pressure. Dust also plays an enormous role. Mars experiences colossal dust storms that often begin in the southern hemisphere during spring and summer. Sometimes these storms grow to global proportions, cloaking the entire planet in haze for weeks or even months. These storms not only alter temperatures, but also affect solar heating and the transport of water vapor. Studying them is a major science goal, because they reveal how Mars' climate works on both short and long timescales. But what can the current climate reveal about the past? To reconstruct Mars' climate history, scientists combine present-day observations with models and geological evidence. Monitoring the planet over one full Martian year 687. Earth days and repeating these observations over several years helps scientists track seasonal and interannual variations. The data gathered allow them to refine climate models and extend their understanding back through time. One especially valuable archive of Martian climate history lies in the layered terrain of the polar regions. Much like tree rings on Earth, record seasonal cycles and long-term environmental changes, these polar layers preserve a timeline of Mars' atmospheric history. Each layer holds clues: when it was deposited, whether conditions were warmer or colder, wetter or drier, and how volatile materials like water and carbon dioxide shifted over millennia. By drilling into these layers or analyzing them from orbit, scientists can reconstruct the ebb and flow of Mars' climate across millions of years. This leads to deeper questions. Was Mars' climate ever like Earth's? Did the planet once support lakes, rivers, rainfall, or even oceans? Geological evidence suggests that billions of years ago, Mars was warmer and wetter, with surface conditions suitable for liquid water. If so, what happened to transform Mars into the cold, arid desert we see today? Did the planet lose its atmosphere due to solar wind stripping after its magnetic field weakened? Did changes in volcanic activity alter greenhouse gases? These mysteries drive current missions and fuel future exploration. Ultimately, unraveling Mars' history of water, climate, and habitability is central to one overarching quest: to determine whether life ever arose there. Each rover and orbiter adds a new piece to the puzzle. From identifying promising rock samples to mapping the climate system, from detecting organic molecules to probing polar ice layers, every mission moves us closer to answering the profound question of whether we are alone in the universe.